I want to talk today about the reduction of alkynes, and as much of the chemistry of alkynes is similar to alkenes, our first instinct might be to try to do some of the same reactions with alkynes that we do with alkenes. For instance, we might try to do a catalytic reduction of the alkyne using a transition metal catalyst like platinum and H2. And you can do those reactions, and the product of a reaction like this is the alkane, where two equivalents of H2 have been added, and we've completely reduced our pi bonds. So as an example of this, you can take this aromatic alkyne, reduce it with platinum and hydrogen, or you could use palladium and carbon and hydrogen, and you get ethyl benzene. What's happening here is clear. Our initial alkyne is reacting with the hydrogen that's been activated by the platinum to form a double bond. But we know that alkenes are also reactive with these conditions, so the reduction continues until we go all the way to our alkane. First, one of the pi bonds is reduced, then the second one is reduced. What if we wanted to stop here, though, with our alkene? What if we wanted to go from a triple bond to a double bond? How do we do that? Well, what we need is a catalyst that is reactive enough to reduce the first double bond, but not reactive enough to reduce the second double bond. What we need is something called a poisoned catalyst. Now that's kind of a dramatic sounding name, but what the poisoned catalyst means is that we've done something to the catalyst to make it less reactive. Now there are a number of things we can add to our catalyst to make it less reactive. The most common set of chemicals to add to make the catalyst less reactive is lead acetate and quinoline, which is an organic amine. So the palladium is the catalyst, it's absorbed on calcium carbonate, and the lead acetate and the quinoline make it less reactive so that it can only reduce the first double bond, the first pi bond, but not the second. The name of this catalyst is named the Lindlar's catalyst, presumably after the name of the scientist who discovered it, but it's very useful for going from an alkyne to an alkene and stopping the reduction there. So as an example, we can take this alkyne, H2, and the Lindlar's catalyst, and we'll add one equivalent of hydrogen gas to it, and we end up with our alkene. Another example is if we take this aromatic alkyne, react it with Lindlar's catalyst and H2, and we get this alkene again. One thing I want you to notice about both of these cases is that we end up with a cis alkene. Another way to say it is it's a cis double bond. Both hydrogens are added to the same face of the double bond. In other words, we get syn addition of the H's. And that will always be the case when you do a catalytic hydrogenation with the Lindlar's catalyst. We'll end up with the cis double bond, both H's added to the same face of my triple bond. And if you want to visualize why this is, we can look at sort of a schematic of the catalytic reaction. So if we look at the schematic of the catalytic process, the hydrogen gas comes in, it lands on the surface of my catalyst, it kind of splits the bond between the two. We have two hydrogen atoms on a flat surface. The alkyne approaches from the top of the catalyst. Since both of these hydrogens are pointed at the same side of the alkyne, when they get added to the same face of the alkyne, and we get cis addition, or syn addition I should say, and a cis double bond. Now that's great and all if we want that syn addition of hydrogen, but what if we want to trans substitute a double bond? Is there something else we can do to accomplish that? And the answer is yes. We can take our alkyne and we can react it with a mixture of sodium metal and liquid ammonia. And when we do that, we get the trans substituted alkene. Now, in order to understand the sort of mechanism of this reaction, you need to realize that the sodium is a source of electrons. And that's what it's going to do. It's going to add electrons to my triple bond. So let's look at what happens. So my sodium adds one electron to the triple bond, and one of the pi pairs of electrons moves to the other carbon. So we end up with this radical. Now this pair of electrons here reacts with one of the hydrogens on the liquid ammonia, as shown right here, to give us this, and then the process essentially repeats itself. Sodium adds another electron to this molecule, give us this, which takes another hydrogen from my ammonia to give us our product. You'll notice that the trans stereochemistry is established way over here in the first step when the radical comes in from one side and the lone pair of electrons ends up on the other side. The important thing for us in using this reaction is whenever we use sodium with liquid ammonia, we're going to get the trans-substituted alkene. As an example, we can take this aromatic alkyne, react it with sodium and liquid ammonia, and get the trans-substituted alkene product. So we know now ways of making both the cis-substituted and the trans-substituted alkyne, as well as how to reduce an alkyne all the way down to an alkane.